Hi team, here we go with the final video in my series on descriptive statistics. And if you want to see any of the others, you can check out the link I'll put in the description below, which will be the playlist for all of the descriptive stats videos. But this one's to do with covariance and correlation, and it's put up on this right-hand side here because it's not a measure to do with one variable. It actually is concerned with the relationship between two variables. So it's not typically part of a standard suite of measures you'll get for descriptive statistics. But nonetheless, it's very important. So I'm going to give you the intuition behind covariance and correlation first. And then we're going to look at the two scenarios where this measure actually pops up. The first of which is where we have a sample and we're trying to assess the covariance or correlation between two variables. And the second is where we're given a discrete probability distribution to work with. And I'm actually going to go into Excel and try to calculate covariance and correlation and show you a little bit of the Excel wizardry as well with Excel formula and the like. But let's jump into the definition. Covariance and correlation both describe the relationship between numerical variables. So for example, if I have temperature measured in Celsius, and let's just say our second variable is ice cream sales. Now it's quite clear that as the temperature goes up on a sunny day, we might see that ice cream sales also goes up at the same time. So the fact that they're moving in the same direction indicates what we might call positive covariance, or indeed positive correlation. They're moving together. That is the crucial thing to take away for the moment. So let's imagine now we have a different variable too, and let's say we have pneumonia presentations. So one might think that as the temperature goes up, we actually have less pneumonia presentations, because I guess pneumonia is something you suffer with generally when it gets quite cold. So the fact that these two variables are moving in opposite directions indicates some kind of negative covariance or negative correlation. And finally, I was trying to think of a variable that has no correlation with the temperature outside, and I came up with the stock market movement. I think it's probably safe to say that the temperature doesn't really affect the general stock market movement. I'm pretty confident in saying there'd be very little or no covariance or correlation between temperature and the stock market movement. So what's the difference between covariance and correlation? Well, I think that's best exemplified by using an example. So let's move on to seeing how they're calculated from a sample. So here we have two variables, x and y. And we've got 5 different days on which they have been sampled. So on day 1, let's just say this is stock x was $30, stock y was $5 on day 1, and then on day 2, stock x jumped $5, stock y jumped $3 to go to $8. Now the first thing we're going to do is find the mean of the x variable and the mean of the y variable. And these are both quite trivial to find, I'm sure. Now the objective here is to try to find the relationship between the two variables. But we've got a problem because x's numbers are quite high and y's numbers are quite low, so we can't really just compare them. We're first going to have to find the deviations from the mean for each of these respective values. So each of these columns takes away the value of the respective mean. And you can see we've got x bar here and y bar in this column, meaning the mean of x and y respectively. So for day 1, x was 3 values below its mean. It was 30 where the mean was 33. And y was 1 value below its mean, and so on and so on. So what we really want to do is compare these two columns, because if they both show the same signs for each day, that'll tell us that they're probably positively correlated or have positive covariance. But if they tend to show differing signs, like they do in this final day, if that was more common, you might say they have a sort of negative correlation or covariance. But how do we then actually calculate a numerical measure? Well, no surprise, we then have to multiply them both together. And when we get positive numbers in this product here, that tells us that they must have been the same sign. And when we get negative numbers, that tells us they must have been different signs. So this is clearly going to help us then calculate some measure of the relationship between the two. And indeed, that's what this covariance formula does. I've written cov xy, which is the same thing as saying sigma subscript xy. You might see it written like that. And all it is this sum of this final column divided by n minus 1, which is in essence some kind of mean, some kind of average value for this final column. So you can see that we're going to get 35 if we sum up the final column. And because that's positive, you'll notice that when we calculate this, we actually get a positive value for covariance. There's 5 values in the sample, so n minus 1 becomes 4, and then we get a covariance of 8.75. But I hope you can see that if these numbers in the final column were mostly negative, we'd actually get a negative sum and therefore a negative covariance. So with that, we can say that x and y are therefore positively related. Unfortunately, this won't tell us the strength of the relationship. All we can tell is that it's positively related. Now, an obvious question that I'm sure is coming is why did we divide by n minus 1 and not just n? Well, that's to do with a topic called degrees of freedom. And I've covered this extensively in a video which I'll link to in the description. But my cop-out answer, my shortened answer for this video, just asks you to look at what would happen if we only had one observation in our sample. Imagine we just had data from day 1, the 30 and the 5. You'll notice that by definition, x is going to be its mean and y is also going to be its mean. So there's no way we can actually calculate a covariance. It becomes a completely moot calculation, and it's only when we have day 2 that we now have what's called 1 degree of freedom. So we'll be able to divide by 1. Anyway, that's my real quick and dirty answer for you. If you're unsatisfied, check out the video on degrees of freedom. Link posted below. But let's continue. Before we calculate the correlation, I thought I'd just show you how covariance compares to variance. You might have seen this formula quite a lot. That is the formula for a variance from a sample, the sum of x minus x bar squared over n minus 1. You'll notice that it looks very similar to the covariance formula if you just replaced y with x. In fact, it's exactly the same. So I thought I'd just bring this to your attention because you might think, where does this covariance formula come from? Well, it's just the variance formula, but just done with 2 different variables as opposed to 1 variable. Anyway, let's continue now and have a look at the correlation and see how it differs. Correlation is given the symbol rho xy, and it's actually the covariance. So don't forget, this was the covariance on top here. The covariance divided by the product of the 2 standard deviations. So let's calculate this and then we'll discuss why we've divided by the 2 standard deviations. So the covariance was 8.75. That's what we calculated in the last slide. The variance, or I should say the standard deviation of x, we can find that just using Excel or just chucking these into a calculator, whatever you'd like. And the same goes with y. And when we get this value of 0.820, this tells us that x and y are positively related, but particularly it gives us a measure of strength because by dividing by the 2 standard deviations, we actually get a number that's between -1 and 1. So a correlation of 1 means that the 2 variables are perfectly positively correlated. A correlation of -1 means they're perfectly negatively correlated. And a correlation of 0 means that they're completely independent. 0.820 is quite high, so we'd say that they are strongly positively related. Now you can totally calculate this purely by using Excel formula. You don't actually need to go through this long process. I just tried to show you what's under the hood, so to speak, of these Excel formula. But if you try to find covariance of 2 variables, you can write equals covariance.s for a sample. And then in here you put the 2 arrays, which would be the x vector and the y vector. You would just put the cell references in there, and that would find you the covariance, and this will find you the correlation. And again, it's a correlation of a sample. It just so happens that you don't need the .s for this particular Excel formula. So that's it. That is how to calculate from a sample. What I'll do now is I'm actually going to take you out of this environment and have a look at Excel, because I've actually got in Excel the calculation for a discrete probability distribution. So this one has to be done somewhat manually, and that's why I've taken you to Excel. Also to show you how to use some cool Excel formula that might help as well. So we've got here X and Y, and we've got what's called a discrete probability distribution because there are 5 discrete outcomes, each with their own probability of occurrence. And you can see X and Y have their respective outcomes here. Now, you might look at these and notice that they're actually acting in different directions. When X is high, Y seems to be low, and vice versa. So right away, we might be expecting a negative covariance or negative correlation. Now, each of these probabilities have accorded with some kind of market outcome. Let's just say these are stocks again. So if the market is booming on a particular day, X goes up $10. Y goes down $3. So Y happens to work probably in the opposite direction to the market as a whole, which happens with quite a few stocks actually. Anyway, again, we're going to try to find a numerical way of assessing the relationship between X and Y. So much like the sample version in our previous example, we're going to have to try to find the mean of X and Y first. In this case, we can call it the expected value of X. And it's a similar reason as for the previous example, because we can't just compare the raw values. We need to assess whether these values are higher than the mean or lower than the mean. And so we need to incorporate the mean, right? So let's find the mean of X. So here I'm going to write equals sum product. And if I go sum product of X and the probability of X, and you can see I'm just clicking and dragging those cell references, putting a comma in between. What that's doing is it's taking each value of X and multiplying by the corresponding probability. That's effectively weighting each of the values of X by its probability of occurrence. And the fact that we're doing a sum of the product means that we're adding the resulting values, meaning that our final answer here when we add them all together is in fact our mean of X, our expected value of X. Now that was just using this fancy formula that you might have seen before, but you'll know with me on this channel, I tend not to use formulas too much because I want you to develop intuition. I hate the idea of people just applying formula without due understanding. So again, for Y, we can do the same thing. We can write equals sum product. We open a bracket, we select the Y values, and then we select the probabilities. So the mean, or I should say the expected value of Y is 1, whereas the expected value of X is 2. Nice round numbers, pretty convenient, wouldn't you say? So, like last time, we're going to need to find the deviations from the mean. So this 10 we have for X, how much does that differ from the expected value of X? We can tell that it's 8 values higher than the mean. The next one down here, well, that's 4 values higher than the mean. This one's 1 value higher than the mean because it's 3. 3 minus 2 is 1. Now we have minus 8, which is 10 values lower than the mean. And this one's 17 values lower than the mean. And we can keep this up. So this provides us with a similar situation to the last example, where we have the deviations from the mean for X and the deviations from the mean for Y. And again, we're going to want to multiply them together because ultimately when they're going in the same direction, that tells us that the variables are positively related. But if they're going in opposite directions, as most of these look like they're doing, then we know that's probably going to be a negative correlation. So let's find out. So here I can simply go equals that cell times that cell. Sorry, it's whited out my formula there, but you just go equals one cell times the other cell. And then you can drag that down. Pretty nice. So if we want to find the covariance, we're going to have to do something similar to what we did in the previous example, which is find the average of these products. However, don't forget this is not data from a sample. This is a theoretical distribution that has a probability associated with each of these outcomes. So that's why the formula looks a bit like this. We take that product and we multiply by the probability each time before we add them together. So we're essentially weighting each of these outcomes by the probability of their occurrence. So we can go straight now down to our covariance here and go, well, what is the covariance? It's going to be the sum product of this array. I'll highlight that, comma, and then I'll put the array that has our probabilities. Boom, we get a covariance of minus 21. Is that big? Is that small? Who knows at this point? We're probably going to guess it's quite big, only because by eyeballing the data, it looks like they really are going in opposite directions quite strongly. But as we said before, covariance doesn't really give us an indication of strength of the relationship. All it tells us is whether it's positive or negative. And indeed, this one turns out to be negative. So the next thing we're going to have to do is find the correlation. Now you'll notice that in the correlation formula, we need to find the standard deviation of both x and y. So that involves a two-step process involving finding the variance and then taking the square root to find the standard deviation. So if you recall the variance formula for a probability distribution like this, we first square each of these deviations. So if we're going to do it for x, we take each of these observations and square them and then multiply by the probability. Because don't forget, we're weighting each of those squared deviations by the probability of occurrence. Now I'm going to do it a very cheeky way, which is going to shortcut a lot of the squaring. I'm going to do another sum product. I'm going to do a sum product of the x array. I'll put a comma. I'm then going to select the x array again. What that's going to do is it's going to multiply each of the values by itself. And then when I put a comma for the second time and select the probabilities, it's essentially going to be going, all right, let's take 8, times it by itself, and then times by 0.15. And then add that to 4 times by itself times 0.35. So I've done it in a way that minimizes the number of columns I'll need to make. It's a bit cheeky, but hopefully you can follow me and you're happy that that works. So I can do the same thing for y. Now to find the standard deviation, I'm sure you could tell me you just take the SQRT equals SQRT and we click in the cell above. And that gives us 7 for the standard deviation of x. And if we want to do it for y, I'm just going to drag that across and we get 3.1. So we can then find the correlation for xy, which is going to be equal to the covariance, as per the formula, divided by the two standard deviations multiplied together. And look at that, we get a very, very negative correlation, very close to -1, in fact. So minus 0.94. That tells us that x and y are very strongly negatively correlated. So a final question I might field at this point is, why didn't we have the problem of degrees of freedom in this particular setup? Why did we have to worry about n-1 when we're taking a sample, but we didn't have to worry about n-1 here? We just multiplied by the probability and that was considered enough. Well, that's because this is a theoretical distribution, a theoretical population distribution. 15% of the time, this is the outcome. 35% of the time, this is the outcome, etc., etc. We haven't been given a sample from which we've estimated the respective means. And that's why I've used the expected value of x here as opposed to x bar, and the expected value of y as opposed to y bar. Because x bar and y bar respectively are estimations of the mean, estimated from a sample. And when we use estimations, we add extra uncertainty in our calculations. And for that reason, we need to account for that extra uncertainty by subtracting 1 from the denominator, making it n-1. And that inflates appropriately our calculations of variance and covariance. But in this case, because we have a population distribution, we don't have that issue with having x bar, so we don't need to worry about n minus 1. Anyway, that is it. That is the end of the covariance and correlation video, and in fact the end of the descriptive statistics video series. If you liked it, please subscribe to the channel. You can click the little icon in the bottom right and like the video and show it to your friends as well, because that's the only way that this channel can grow and give me the impression that it's worth more time investing into making videos for you. But thanks for listening. My name's Justin Zeltzer, and you can check out all my stuff on zstatistics.com. I'll catch you later.